Okay, thank you, Shima. Thank you, the organizer, for having me. Long time since I met so many friends at outside of my own department. So what I will talk about here is sort of, you could say, ongoing work with a number of my students and a few other people. And it revolves around these operators, which are parabolic, second order. And it's important to note that the matrix here is allowed to depend on time as well as x. We have ellipticity. These are complex valued operators. So we have coefficients that are complex and they are accretive in the sense stated. And as you can see, there is a weight in there. So strictly speaking, I will discuss also the case when the weight is equal to 1, unweighted. And then there will, of natural reasons, be weights popping up. And the things I will discuss then when it comes to the weight is that the weight is Markenhaut A2. Important to note that the weight here is independent of time. It's a very interesting but completely open how to work with these kind of problems when I have time-dependent weight for, to some extent, obvious reasons, how to define solutions and so forth. So, let me see, I try to do this. Yeah. So with one of my students, Malte Lidskord, I've been interested to look at, if you look at the unweighted version of this operator, you take powers, not integer powers. You take an S here, 0 to 1. How to make sense of these operators in this generality and particularly see if you can somehow attach this operator to a local equation by looking at an extension problem. So in this case, you add a direction, the lambda direction. So you go from xt, add lambda direction, and you try to see if you can construct some kind of extension up to the upper half space, starting from your initial solution, such that this sort of generalized Neumann, digital Neumann map is related to fractional powers. So this is sort of outline, motivation, and summary. So this is what we have been working on. And if, so these operators here, you can see if you're on this upper space here, this lambda to 1 minus 2s will be an A2 weight. So it leads you from this, but also for many other reasons to study weighted operators of the nature I had on the first slide. And as we know now, I mean, if you want to study develop potential theory and solve the boundary value problems for weighted operators or non-weighted, where we don't assume symmetry and so forth. A key estimate to get certain programs going is to prove Kato type estimates. So in this case, we've been interested with another student, May, Olivier Tay, and Moritz Eggert, to generalize what Pascal Aucher, myself, and Moritz did in the unweighted case to the weighted case with this particular weight. So now the mu here is basically you take just the weight, dx dt, and this is just an energy space, which we probably will discuss. So what we can prove this, and perhaps not too surprising, but it's sort of interesting the way we do it is that we just use second order techniques compared to the proof Pascal, Moritz, and I have, where we look at a first order system and actually prove much more. So this paper sort of is being revised now and then, and we sort of discover interesting details all the time. The point is to prove this estimate, making as little assumptions as possible and so few estimates as possible. And at this point, it seems like the original proof I had in the time independent case, which then goes back basically to the work of Pascal and Steve and others in their original Kato paper, you can actually handle the time-dependent case quite similar with the same kind of test functions in the Carlson-Meshter estimate. We sort of an interest. So this paper will be pure second order, and it seems at this point that it will be quite in line with the elliptic paper, and that you can handle sort of the time derivative using Littlewood-Paley theory and related things. So this is sort of what the sort of context that we've been working in. So I should say there are many open problems here related to, in particular, boundary value problems. So what I hope with this little talk here is that some of you might be sparked to do more and do better, and be interested in parabolics and perhaps even in weighted operators, which when I was younger, I thought, why should I weighted operators? Now I understand that they were really relevant from a lot of perspectives. So let us go back to motivation for this. So if you look at the fractional Laplacian, which is a key player we know in potential theory, relates to Levy processes and so forth. There was this sort of a nice paper by Luis Caffarelli and Silvestre a number of years ago, where they show that you can sort of realize the fractional Laplacian as this Dirichlet to Neumann map if you look at an extension problem in the upper half space of exactly the nature I had on the previous slide, but now we're in the stationary case. So what they proved is that if you solve this problem, and actually, this is like a Dirichlet problem in the upper half space, just add this direction lambda, then actually this generalized Dirichlet Neumann map is exactly the fractional Laplacian. So if you look at S equal to 1/2, then you just have the Laplacian. And we know you can do a lot of file in that case because you sort of relate it to the square root, and you have like e to the, say, minus lambda square root. Take the derivative, sort of comes out quite natural. So this more interesting, and the more interesting case is when S is different from 1/2. So what they did then was that by this localization, suppose now that the fractional derivative, fractional Laplacian is 0 on some domain, that means that this Dirichlet to Neumann map is 0, this set. But then you can do an even extension over the boundary lambda equal to 0 to get the solution over this extension boundary. So what it then happens to be in, you're in a situation where you have solution to this sort of the energy elliptic equation with an A2 weight, and you can derive estimates for solutions to the fractional Laplacian equal to 0 through this degenerate elliptic equation. And those estimates were done a long time ago by Koenig and others in a sequence of well-written fine papers, so you can take that out to the shelf. So that must sound like a really great innovation, right? You can do this. But then, of course, if you localize, you get this problem with the boundary. So even though some of the results might be striking, if you look in the probabilistic literature, they prove everything in open sets. Because if the underlying process now is the Levy, it makes jumps. So the presence of the boundaries is not that much of an issue. So by localizing, you get into other domains, so to speak. But on the other hand, you have to assume strong result on the domain. If you're in a probabilistic setting, well, you don't use analytic tools, but the domain is of lower order. So for example, boundary Harnack inequalities for this comes from the context of Lipschitz or anti-A domains if you do the localization. But the probabilistic guys or females, they prove it for open sets. So you gain something by localization, but you also lose something. So there also been a lot of work in the operator theoretical context. So we're trying to analyze this. Suppose now that you have a sort of, you can pose the question, if you have an operator sectorial on the boundary space, can you construct solution to this? Then function space value of the E, such that you can make sense of the Neumann map, getting the fractional power of the operator. So a lot of activity in here, and sort of boils down to whether or not you can do it, sort of is related to sort of how to construct certain semigroup related to A. So if the operator is sectorial with angles less than pi divided by 2, you're in the context usually of analytic semigroups, you can make use of that and so forth. But there's been a number of works in this area which are quite interesting, which do not really relate to PDEs, but look at it from a more operator theoretical perspective. So then you might ask, what about parabolics, right? So there are many versions of the fractional Laplacian if you add t. One is this: you add just a time derivative. You're in again this Levy stable processes. And if you know something about finance, already in the 60s was observed by Mandelbrot, studying the prices of cotton, that a large move in an asset of cotton in this case is much more likely than what the Gaussian usually predicts. So then there is a large literature how to remediate this, introducing more sort of advanced model, you might say. One is to look at where the asset is driven by a Levy process having fatter tails, and then you end up actually solving the Cauchy or obstacle problem for this type of operator if you're going to price options. Another is that you might add a fractional time derivative. It's interpreted as a stochastic process where you have certain memory in your model. There'll be some activity in that. Then another thing is, of course, you can take fractional power of the heat operator. And that's closely connected to something called this continuous time random walks. It has been studied in particular in physics, goes under the name anomalous diffusions. And it's anomalous in the sense that, in this case at least, space and time is coupled, which is not the case in these models upstairs. And so I just want to make that point. If you look at this and these underlying stochastic processes, there's the fundamental difference is that in this case, space and time are intrinsically coupled. So in this case, it's sort of that the random, you have a particle, I have a slide, I might discuss that. You have a particle that is sort of moving after certain waiting times. And then the way it moves is that it's drawn from a Gaussian with volatility or standard deviation determined by the waiting time. So let us just look a bit at this, the fractional heat operator. Defined on the Fourier transform side, you can write it out as an integration toward the kernel. And you see the kernel here is the usual heat kernel, but for fixed tau, sort of fixed waiting time, the tau enters as the standard deviation. And then you have this part of the kernel coming from the waiting time distribution. So you can write out this operator explicitly. And just to note that, of course, if S goes to 1, by this normalization here, you will recover the heat operator. So this is what I said. I just found, usually I think this is if one were able to, it would be great to master both the analytic and the probabilistic perspective. And what I think, at least from my perspective, start to look at this, it was a completely unknown field of probability, this continuous time random walks. And there is a lot of interesting work going on in that field, which sort of relates, and there is good openings, I think, for people in analysis to look at those processes and connect them to analysis and vice versa. I just want to emphasize what this sort of the continuous time random walk is, that you have a time which is random, which sums up the first m times where the particle jumps, and when it jumps, then it's a jump with some according to some distribution, and then if you write it out, strictly speaking, you will get the particle moving at certain waiting times. It will jump, and sort of if you look at from the financial perspective, you could also think this is sort of a loss process. So it's continuous time random walks, that's what it's called, but it's also usually called a renewable process or queuing process. So then, of course, the question is what kind of assumptions you make on the YE, if these are going to be coupled or decoupled and this kind of stuff. And what sort of seems to be rather deep results in the field is that in the same as you look at standard random walk, you can look at some so-called scaling limits of those, and then you get Brownian motion. In this case, there are interesting work by a number of people in probability showing that you can do scaling limits at the same way as you sort of do it for Brownian motion. And then the sort of limiting process will sort of have this Levy measure where you see exactly that the coupling between waiting time and the standard deviation for which how much the particle deviates. So the density here is then the same density as appearing here. So why is all this interesting? Was because a number of years ago I was talking to some people saying what is parabolic analog of this Caffarelli-Silvestri's approach, right? Which has been I must say quite influential. And then I had a student back then, and one day after having had a great lunch at the gas station in Sweden, I actually started to do some calculations, and I discovered this not as polished perhaps as stated here, but that if you look at the fractional heat operator and you have a solution solving this now, so look, as this is exactly the Caffarelli-Silvestri PD, but you replace it, the Laplacian, with the heat operator, then if you look at this so generalized Neumann derivative, Neumann map, you actually recover the fractional heat operator. So from that perspective, if you want to localize some kind of fractional heat operator, this is a good operator. So what you then can do is that you can do the same trick. You flip over the boundary. So if you want to derive local properties for solution to this equation, you can use that. You can do that by looking at the corresponding questions for now this degenerate parabolic equation. And then sort of a lot of estimates for these kind of operators, at least, you know, on the Moser Nash the Georgia level, was done by a student of Fabe's many years ago. They developed some of this parabolic analog of the program Kenigan, Fabe's, and Serapione and other had. What is interesting here is that in the elliptic case, the people in probability, they can prove a lot. It seems like from our perspective, the corresponding probabilistic theory is rather unexploited in this context. So let me just say something about how do you do this extension? And I should say this is not as polite. I didn't do it this polished at that gas station, but the idea was sort of similar. The thing is that you introduce here what is called will be a semigroup. Stated as follows: if you let tau go to 0, you will recover u at xt. And then you let tau be positive, it will have the properties of a semigroup. And actually what will happen is that you take the tau derivative of this guy, then you add the heat operator, that will be 0. So you're solving sort of the ODE you usually have when you study semigroup in the upper half space. And this will be a solution to that with the operator being the heat operator. Using that, you can formulate the fractional derivatives or fractional powers of h as stated. Then you do this extension in this way. It's not necessarily a unique way to do it, but perhaps there is, I don't know. But at least if you do it this way, this guy will solve this PDE I described, and you can prove by going to the limit that this is the case. But what does this emphasize? It emphasizes the importance of introducing some kind of a semigroup related to this time-dependent operator. And I mean, usually when you look at semigroups and so forth, you tend to have a stationary operator, and then you add time, right? Now we have an operator, we have space and time already, then you add one more direction, which is of course okay. And then it turns out that this is a valid extension. So what Malte and myself was interested in is to sort of see to what extent can you go for these kind of questions or this kind of extension for this quite general operators, right? Where you have the context I described, you just assume bounded measurable complex coefficients. how to introduce the fractional powers. Could you make it some relation to some kind of local problem? And then potentially study sort of local solutions to these equations, making, we assume real coefficient, can you prove sort of Harnack inequalities and this kind of stuff. So the point here would be in particular that even though we might be interested in real coefficients, you somehow to make sense of all of this, the operator fractional powers, you have to go to the complex context. And if you can do that, you sort of should be able to handle both non-symmetric and time-dependent coefficients. And that's sort of different than compared to the case where you have sort of your standard elliptic operates just at time, right? Because in that case, semigroup structures and theorems comes quite naturally. So somehow, in this context, you have considerably less tools, and it's completely less clear how to define even these fractional powers. So I should say that all of this somehow, starting from the second slide, or third slide perhaps, concerns trying to continue somehow the program I and then Pascal and Bouchard and Maurice Eggen started concerning Kato and boundary value problems for these type of operators. So one way then to this, in this generality, to make sense of this operator is to look at it as an operator on this energy space, which turns out to be relevant to study parabolic equations. So we have a Hilbert space, everything is complex values. We look at this energy space, we see you have basically the fraction, the half order heat operator over here. So you have gradient with respect to x in L2, then you have this half time derivative. This is the energy space. So you have a triple of spaces here. You have Hilbert space H, you have this Hilbert space, and then you have its dual or anti-dual. And then you have this triple of spaces, or this means they're continuously embedded in each other. So what we sort of, yeah, let's go. So then the question is how do you define this operator H, right? So we have this condition now with coefficients. We study this operator, which is sort of the operator you get when you sort of look at the weak formulation for these parabolic equations, but you sort of split the time derivative into two pieces. And what you then get is that you can place one half of the derivative on the test function, if you prefer. And then you will have also this term, but you have the Hilbert transform, so that when you move this over, that adds to the half-time derivative. So what you then do is that you introduce this operator now via this form. So in this case, you get an operator from V to V prime, defined as stated that H acting on U, and then you take the V and then you look at this duality. You define that using this form. So the operator gets induced by this bilinear form, sesquilinear bilinear form. Then of course on H, this will be an unbounded operator, but then we consider its restriction to a subset of V. And the functions in V is such that this object here is actually in L2 itself. So, of course, if you study operator theory, the key thing is also to make sure you know what domain you're working on. So what this does is that sort of induces sort of implicit boundary condition on your functions, so that this HU defined like this, in fact, is a thing in L2. So this is the space on which, the domain, I should say, on which we consider the operator written H. So then the question is, how do you somehow get hold of some information of this operator? Then there is this initial insight, which I sort of partially had, but I wasn't completely familiar with all the operator theoretical lingo at that point. But the conclusion here is that this operator now with this domain is what you call maximal accretive, which means that it's closed. And for all sigma now on the negative real line, this operator is invertible. And you also have some kind of estimates on the resolvent at state. So somehow you have a spectrum in potentially all of the one of the positive or real, positive or negative. Basically, you have the spectrum is sort of it's a sectorial of order of angle p1/2, so to speak. But you don't have much more. But this is still a sort of a starting point for that you can do something with this operator on the energy space. And what this result is how it's proved, and it's actually proved in a paper by Pascal and Moritz. It uses this idea of hidden coercivity in this operator H, which was a key insight, which actually Steve Hoffman and Jan Lewis had before. And it turns out to go even back to the 50s by a man called Kaplan, as discovered by my co-authors. But this helps you then to get going, right? If it's maximal accretive, you can make sense. There's a functional fallacy. You can make sense of fractional powers and so forth. So in particular, for example, there is this Laplacian representation where you can represent, at least if U is in this domain D, represent the fractional powers in state. So this is the operator we work on. So in this abstract setting, if I may call it that, you introduce the operator H, written H as stated, and it has a certain domain. So then the question is, can you connect this to some kind of ODE, which involve the so-called local operator H? And of course, the conclusion will be yes. That's what I'm partially going to talk about. So what we say here that this U, written U lambda now, so sort of lambda as a parameter if you prefer, is a solution to this equation for all positive lambda, starting with some initial data. If it sort of will be smooth in the lambda variable, and for each lambda will take value in this domain D, and such that the equation is satisfied in this sense. And note now that this then is by definition given by this form I had on the previous slide. And then of course you want it to be the boundary data to be assumed. So for example, this is going to be assumed in H, but you note here that I have a continuity up to lambda equals 0 here. But then of course I have smoothness just away from the lambda equals 0. So the smoothness here in lambda, of course, is nothing strange because the operator that you start with H is independent of lambda, right? Just add this direction. So the question is now, how do you somehow go about trying to construct some given you some extension, right? That's potentially satisfy this. And as I said, it's fundamental to the topic is the concept of semigroups. And depending on the operator, you can have more or less strong semigroups. And in this case, since we just have that H, written H is maximal accretive, the only thing we know is that A minus generates a strongly continuous semigroup contraction, which is, of course, much weaker than if you had a, say, analytic semigroup or so forth. And I should say, and when I mentioned this, that there is operator theoretical aspects on this extension problem, there's some really interesting papers by, in particular, in my opinion, Wolfgang Arendt and others, where they look at sort of exactly the operator Steve and I looked when I looked at the Kato problem, and they look at these extension problems, the Dirichlet normal map in that context and so forth. And I worked quite hard trying to do that kind of paper in the parabolic case using the idea of hidden coercivity. But so far I have not been successful. So what we do here is that we basically try to proceed with this rather weak semigroup. And of course, our result will not be perhaps as strong, but it might be a starting point for further development. So this is a theorem then. Take S. You have the semigroup. You define this operator depending on parameter lambda. Then you take a U, which now in the domain that I started, the domain of that is sort of everything is built on. Then this U lambda is a solution in the sense discussed on the previous page. And then here I have some results which perhaps you don't have to care too much about. But what is important is that you see in this estimate here of this sort of Neumann, digital Neumann map, if this is an L2, this is finite. That's where, for example, that enters in particular. So that's the reason I bring it in here. You want to go to the limit there, of course, it has to be finite. So what you then prove is that this is in fact the case, that you get this fractional generalized heat operator through this Dirichlet Neumann map in this rather abstract set. And note here, and that is really important, right? That U is all the time in this domain here. And what it all boils down to when it comes to complexity is for what domains can you do that? What is the domain of this guy is sort of should be different, right? From this set of functions. So this might look good and it's sort of interesting, but I would say that there's room for extension to sort of less severe assumption on U. So then the idea was, well, suppose you can do this extension, right? Can you establish some local regularity estimate for solution to HSU equals 0? I here say that you have a weak solution in some domain here. So this is a domain in omega, and you make the cross product with a, say, interval in time. It's a weak solution if this is the case. So what we then do here is that we take, again, U in this big D, do the extension. We do this even flipping over the boundary. And then we prove on these assumptions that this U tilde is, in the language of Pascal, Morris, myself, is a reinforced weak solution to this PD, but now it's in the appropriate weighted spaces. So a reinforced weak solution is a concept stronger than weak solutions. It's stronger in the sense that they are usually controlled then by definition of the half-time derivative in L2, which is, so if you have a reinforced weak solution, weighted or unweighted, it will be a weak solution in the traditional sense. So we flip that over. And in particular, I should say that you have this. If you do this, you have this when lambda is different from 0. But why do you get it over the boundary then? Well, you get it assuming that HSU is equal to 0 on this set. Because then this Dirichlet Neumann map will be 0 there, and you actually will be able to continue the solution. So first of all, you have this when lambda is different from 0, and then assuming this, there is a function U such that this is the case. Then through this Dirichlet Neumann map being 0, you can extend the solution over this boundary. That is a key subtle point in this argument, that's possible to do. Well, then if you go to real coefficients, right, then you have this sort of this, if you might say, standard operator in divergence form with weights, but assuming real coefficients, don't have to assume that they are symmetric or anything. We would then like to make some conclusion about regularity. So in this case, assume that it's real measurable. You take a point, assume that there is such a one, which is a weak solution to this equation. And then you assume that the L-infinite norm is bounded. Note that if you look at sort of these equations, non-local, the Dirichlet problem, of course, assumes data globally. So if I'm now going to make some estimates, which involve the L infinite norm, I basically will have to have the L infinite norm up to bounded in all of Rn, but also up to the point tau 0 plus this, and then all back to minus infinity, because that's where sort of these, the right sort of a parabolic boundary, if you might say, for these operators. So what we then can prove under these assumptions, that you have a Harnack inequality, and then you have this Hölder continuity estimates. And sort of in the end, it boils down to that these estimates were proved by Filippo Chiarenza and Serpione. And of course, again, their results are usually, as they did back then, proof for symmetric coefficients, but it's doable for non-symmetric as well by the standard techniques. And the way we do this is that we somehow need to get hold of some kind of kernel estimate to be able to make estimates, it seems, if you're going to have point-wise estimates and so forth. So what we sort of did, which is perhaps rather standard, is to do the use what is called the the approximation of these operators. So H for minus H is initially not defined on the Hilbert H, but if you make this modification, you have the sigma, which is the degree of freedom. It will be bounded on the Hilbert L2 space. So you can then conclude that this is the case if you think about it. And you can also look at this semigroup, at least in L2, as sort of a limit of this infinite composition of, or infinite sum of, basically what you do here is you take E to minus lambda H0, write that out. And then the thing is that for these operators, you have a kernel, which basically comes from, at least in the symmetric case, originally from Aron's own, but in the non-symmetric case, at least there is more recent work by, don't remember the two Chinese names, which do this in quite a lot of generality, assuming even more general coefficient, just bounded the measurable and so forth. So to get this done in the end, we do a lot of what I felt rather refined limiting argument, where you cut this infinite series, and you do estimates for finite sigma and for finite series. And then you have to let the length of the series and the sigma goes to 0 in the right order, and making sure that things are finite and so forth. So I just want to emphasize this, which could be slightly, it's a very relevant thing, right? To me, at this point, it seems rather unclear this following. Right? Assume that this is a weak solution to that. First of all, this space D is rather abstract, what it is. I mean, how regular are functions in there and so forth, right? It could be, I don't know, perhaps they're already quite regular. So we're trying to prove that a Hölder, right? And the other thing is, I mean, can you somehow produce a solution to this equation in here? And the thing is that, so our result is actually derived on this rather strong assumption, a lot of implicit assumptions, basically, on the operators, the coefficients, and so forth. So what you can say is that you have this, the domain of these operators, HS, is sort of nested as a function of S, right? And sort of at the very heart of all of these is this domain D. And it's what do you say? It's a core for all these domains, meaning that if you take the graph norm, the graph there, and you just look at elements in this, it's dense in the corresponding graph norm of the true domains for this HS. So the question is, of course, how you can do all this just assuming that U is actually in the domain of HS, not in the domain big D. And that's where I sort of originally started out and trying to then to see how can you sort of use this idea of hidden coercivity, which was sort of a big thing in the other things we've done on parabolics, and how do you then refine this construction of extension operator? And I would label that as an open problem, and I will continue to work on it, and maybe it will. Some of you might find it an interesting thing to think about. So I will just skip this and just state something about the Kato problem. I have 5 more minutes, right? Before. So the Kato for weighted operators, this is work done with Ole Reza and Moritz. We look at weighted space. Mu is the weight Wx dx dt. We introduce this form again now on the weighted spaces. So formally, this is the operator. We then prove exactly what Pascal, myself, and Morris did in the unweighted case, but in the weighted case. And the weight is an A2 weight. What I would like to say here is that there are some interesting aspects in the paper that we will complete, I guess, in the upcoming month or so, unless we discover even more things we don't feel completely a priori comfortable with. What I mean by that is that, first of all, you do this purely second order approach compared to what Pascal and myself and Morris did. And of course, that's because in the first order, we prove much more, right? We have to do something with half order derivative. In this case, that is not the case. And it turns out that in my original paper, this one, the time independent case, if you start to do at the final part, you group terms slightly differently. It seems like the proof is actually going through even with time-dependent coefficients. Which is what I'm saying, you have to feel comfortable. I mean, it seems, I was a bit surprised actually by that when we started to discuss it with Ole Reza, and he said, you know, couldn't you do it like this? And then, yeah, it seems like some of the things that got me hooked on the fact that I thought I needed time-independent coefficients seems to disappear. And actually at this point, I should say at this point, it seems unclear if we even need off-diagonal estimate for the half-order derivative. And so it's also say at the end that we seem to be able to use the original test function in local TB that Steve and others invented. So, you know, everything of this boils down to proving what is called a Carlson estimate. In this case, this is the Carlson estimate. And note that we have for this particular operator. And this contains no differentiation in time. So it seems like, as I did originally also, that to prove this, you introduce certain intelligent constructed test functions by Steve and others, which basically looks like this already in the elliptic case. So you just have this sort of composition of x and the direction you're working with. And then you have a cutoff in x and t. That's where the t enters in a very modest way. Of course, it enters as well in here, right? Yes, so that was sort of a brief. So if someone is interested, the first paper is on the archive, which concerned this extension. Then when Morris and I and Alreza is trying to complete the other one. And then actually there is a lot of other things you can do with this connection between fractional parabolic equations and stochastic processes, which in particular you can introduce what is so-called what we call space-time coupled tug-of-war game, which then connects to certain non-local fractional PDE operators, which are basically fully nonlinear. And we have some initial things here, which I think is a big area to work on. It's sort of generalized to the parabolic case and work of Caffarelli and Figalli some years ago. And then these are the other references if you want to get into the kind of problems or Kato problems in general in the parabolic case. So I think I will stop with that, and thank you for your attention.